In the last class, we looked at the differential pair, and let us do a quick recap. So, in the last class we discussed the differential pair and why we needed a circuit like this, right, and the motivation was that when you are building an operational amplifier, the two input the operational amplifier, as you know, is a voltage controlled voltage source, where it amplifies only the difference between the two input voltages, and there is a negative feedback loop that goes and makes tries to drive that difference to 0 ideally, and in practice to some very small quantity. So, as far as the negative feedback loop is concerned, its job is not to worry about what the two voltages are, V in and V out. Its job is only to look at the difference between the two, which is V out times F and V in, and then go and do whatever it needs or whatever it takes to keep that difference equal to 0. So, the first step in the whole process is therefore to design a gain stage where it only amplifies the difference, and all the gain stages we have seen so far are basically the common, for example, the common source amplifier, where we have amplified only a single voltage, and using the intuition behind the common source amplifier, we eventually came up with the differential amplifier. We have done it with NMOS transistors. There is no reason why the same thing can't be repeated with PMOS transistors. And the key points behind the differential pair are, the one is that the two inputs, we know that they are going to be somewhat close to each other or very close to each other. So, rather than talk of two inputs which are almost the same, we talk of them as being the sum of the average plus half the difference and average minus half the difference. The average, of course, it does not look very scientific when you say average. It basically you say what is common to both the signals. So, that is the common mode part of the input signals, and then you have the differential mode. And so, to represent the change in the common mode, we have a small VCM, and to represent a change in the differential mode, we have the differential mode is represented by VD. And we exploited symmetry to analyze this circuit the last time around, and what will be the incremental voltage at this terminal here? What will it be? It is plus Gm times R times Vd plus minus. Yeah. So, if the output resistance of this current source, incremental output resistance, is denoted by RO, then this is going to be R by 2RO times small VCM. And if the current source in the tail becomes ideal, then true to what we desired, we see that the output of the differential pair does not depend on the common mode at all, right. So, once so in principle, once you have let us say we can make we have already figured out how to make a very good current source. We can always use cascoding and things like that to make this gain as small as possible, or make it really small so that it does not bother us, in which case this incremental voltage is simply GMR times Vd, okay. And as you can see in the incremental picture, this voltage here is referred to ground, with respect to ground, it is GMR times VD, where VD is the difference between these two, or GMR by 2 times 2 VD, and so it has taken two floating voltages in principle and converted it into a larger, taken the difference, converted it into a larger voltage, and that resulting voltage is referred to ground. Okay. And then once you want to amplify that, you can put another common source amplifier, or if that gain is not enough, another common source amplifier and so on to get as large a gain as you want, right. So, as you can imagine, the differential amplifier is a key building block in the design of analog integrated circuits and analog circuits in general, and it's because in one form or the other, it forms the input stage of every operational amplifier, which is the workhorse of analog engineering. All right. Now, there is only a small problem with the differential pair. What is that problem? Like in a common source amplifier, the gain is not as large as we'd like it to be, because it's only the output. I mean, if the common mode gain is assumed to be negligible, we see that the gain for differential signals is basically ADM is what we called it, is GM R by 2, correct. And the only way to increase the differential mode gain is to increase the load resistance R, which will basically cause the output quiescent voltage to become lower and lower, eventually pushing the two transistors M1 and M2 into the triode region, right. And the only way to fix this problem is to keep increasing the supply voltage, and as we have seen in the case of a common source amplifier with a resistive load, that is not a particularly efficient way of doing things, because to increase the gain by a factor of 100, you would have to increase the supply voltage by the same factor almost, right, and that is a terribly inefficient way of spending power, right. So, in the common source amplifier, what did we do? Well, we said, after a lot of discussion, we decided that the best thing to do would be to use an active load, right, so not surprisingly, well, we have the same problem. So, the logical place to start is to work with the same solution, right. So, that's what we will do now, and the basic idea is to solve this problem of, and let us assume for the time being that we are not going to be worried about the output. Let us assume an ideal current source, so that if this is VD and this is minus VD, we do not care about the incremental common mode change, right. We will worry about that later. So, we have to increase the gain of the output. So, what do you think we should do? What would we do? What did we do in the common source amplifier case? What did we choose for the load? There we had a PMOS input device, and therefore, we chose a load which was an NMOS current source. Now, what should we do? Well, we have an NMOS input device, and therefore, it seems logical to use a PMOS current source. So, in principle, what we would like to do is to put in here a current source, and what should be the value of the current source? I know, correct, all right. So, basically when VD is 0, well, the current in M2 is exactly the same as the current in current being pushed into the drain, right. And if VD is infinitesimally greater than 0, then what comment can you make? Which transistor, M1 or M2, which will have a larger current? If VD is 0, if VD is greater than 0, if VD is infinitesimally positive, remember that M1 and M2 have the same source potential. So, if the gate potential of M1 is slightly higher than the gate potential of M2, then M1 has got a larger overdrive than M2, but the sum total of both the currents is constrained to be 2 I naught. So, this 2 I naught has to go either this way or that way. If M1 has got a larger gate potential, more of it will go through M1, less of it will go through M2. So, basically if less of the current goes through M2, therefore, the drain current of M2 will be smaller than I naught, and as a consequence what comment can you make about the potential of that node? Current pushing into that node is I naught, current being pulled out of that node is less than I naught. So, that node potential will go up, right, and if M2 and M1 have infinite output resistance, then the incremental gain is going to be infinite, correct. Okay, this is exactly similar to what you would see with the common source amplifier with an active load. Is that clear? All right. All right. So, all right. So, now how do we implement this current source? We connect a PMOS transistor, very good. All right. So, somebody suggested a current mirror, okay, fine, let us do that. If all the transistors are identical, what comment can I make about if all the transistors M1, M2, M3 and M4 are identical, what comment, I mean, does it make sense, or should I, is this, or basically what I meant to ask was, are we okay with this current, or is this not correct? Yes, okay, okay, all right. So, M4, M3 is a 1:1 current mirror, and therefore, I naught will get reflected here, and we are all good to go, right. Now, can somebody stare at this and say, yeah, well, I can do something smarter? Oh, okay, well, basically one suggestion is that, well, these current sources all have to be realized using NMOS transistors, that is a given, correct. So, basically eventually there is going to be one master, I naught, from which you can generate both 2 I naught and I naught. That is not what I am asking, that is not what I am getting at, is can you see some redundancy here and see if we can do better. In other words, can we get rid of that current source I naught and use something that is already there? Okay, so the suggestion is, well, you remove this guy here, and the principle, what is the principle?
VSG will be same for M3 and M4, so same current will flow from both, and 2 I naught is pulling from downside.
So basically what he intends to say is that when VD is 0, right, that is at the point when the differential input voltage is 0, what is the current flowing through M1? I naught, right, okay. So, and what is that I naught doing? What is the drain current of I naught of M1, what is it doing? Is it useful, in other words? At the drain of M2, right. So, do we need the resistor in the drain of M1 at all? Okay. So, if we do not need the drain of, if we do not need this R, we might as well connect it to VDD, okay, all right. So, now you can see that M1's drain current is just simply doing nothing, it is just simply connected to VDD. You might as well put it to work, right. What does M4 need? And what is M1's current, drain current, and what is M1's drain current doing? What is it doing? Nothing. So, what do you think we can do? What can you do? Let us say you are sitting at home doing nothing, man, right? Okay, all right, and you know, you want to order Swiggy from your neighborhood Pizza Hut. Okay, what is your mother going to do? This fellow is sitting at home doing nothing, right? Why waste somebody else's time, like bringing pizza from Pizza Hut to our house? Let's send this fellow instead, right? Isn't it? Okay, that's why you should get a job quickly. You understand? So that's all. So M1 is sitting idle doing nothing, correct? Why get one more current source and then put it through M4? M4 needs a current I naught anyway, right? And this M1's drain current is just doing nothing. So the smart thing to do is to say get rid of that extra I naught, break this character here and connect that guy there. Does make sense, right? I mean, this ain't no rocket science, right? So, all right. So now, of course, you know, this diagram looks terribly terrible. So I am going to redraw it in a slightly different way. So I am going to move all right. So this is M3, this is M4, all right. Okay. Now, let's, so when Vd is 0, of course, there is no difference between the earlier scheme and this one, right. When Vd is not 0, we have to sit and analyze what is happening. All right. So, you know, simplified analysis, when lambda n equal to lambda p equal to 0, when the transistors are all, where the current in the transistors is independent of the drain source voltage, right. So, clearly, so if lambda n and lambda p are 0, basically in English what it means is that the potential at the drains, I mean, by the way, is the circuit symmetric now? Clearly it does not look symmetric. However, if lambda n and lambda p are 0, then what comment can we make? Well, if lambda n and lambda p are 0, that basically means that the incremental drain source resistances of both transistors M1 and M2 are infinite, and in English what that means is that their drain potentials have no bearing on the drain current, correct. So, under those circumstances, what comment can you make about the incremental voltage at the common source node? Yes. What is the incremental equivalent? How does it look like? The current source becomes open, so this is Vd, this is minus Vd, all right. So, the question is what is that incremental voltage? Okay, there are multiple ways of looking at it. I mean, you know, if lambda n and lambda p are 0, you know, as far as the network here is concerned, it is So, what happens at the drain end is irrelevant, right, because the lambda is anyway 0. This is V d. So, this is G m times V d minus V x, and on the other side it is I don't know guys if you guys are following or not. The other side it is G m times minus V d minus V x, and that is minus V d, right, and basically this is V x, all right. So, clearly I mean what is happening at the drains has no influence on what happens below. Therefore, well even though the circuit does not look symmetric, as far as calculation of V x is concerned, this node joining these two halves is concerned. Let's the simplest thing to do is to write Kirchhoff's current law at that node. What does KCL say? The sum of those two currents must be 0. So, the only way the currents can be, the sum of the currents can be 0 is V x equal to 0, understand, all right. So, this incremental current is, this incremental voltage is 0. So, what is this incremental current? G m V d, very good. What is this incremental current? Yeah, it is you write that as minus G m V d going down or G m V d going up. All right, what is this current? What is the current in M4? G m V d, same current has to flow through that diode connected transistor. So, what comment can you make about this current M3? This is sorry, this is M4, this is M3. Okay, what is the current in M3 in the direction shown? So, current is flowing up in M4, in M3, sorry, or maybe it is too small. Is it visible actually? I think not. That is M4 and that is M3. What we are trying to do is find this current. What is that current? All right, okay. So, sorry, let me, okay. So, I guess this is, could be confusing. Okay, let's try and let's try and find the Norton equivalent of the output, the Norton equivalent looking in here. So, what will we do? What will we do? We will find the short circuit current flowing into this voltage source, right. Okay, what is Ix? That is what I want to find eventually. So, Ix clearly consists of two components. One is Gm Vd, that is this character here, all right. There is also the current flowing through M3. Okay. Now, can you tell me what the current through M3 will be? How will we find the, okay, how will we find the current through M3? Okay, what do you need to find the current of M3? The gate voltage. What is the gate? How will we find the gate voltage? Okay, so let us take a look, more careful look at so what is the current flowing here? This is M4, this is ground, this is M3. So what is the current flowing, incremental current flowing down? GM VD. Okay. So incrementally, by now you should know what the incremental equivalent of this character is. It's a resistor of value 1 by GM P. So this is 1 by GM P, all right, and let us call this GMN just so that we separate the two, all right, and this voltage is connected there. Okay. So what is this voltage therefore? Minus GMN by GMP times VD. Okay. So what is M3? The current through M3. What is the model for the PMOS transistor? From in that direction, GMP times VGS will flow. What is VG? Minus GMN by GMP times VD. So this and this goes away. So what is happening? The current is flowing downwards, and that current is exactly the same as GMN times VD. All right. Okay, all this comes out of the math. Is there some way of simply staring at the circuit and saying, "Oh, this is obvious"? So it's a current mirror after all. Remember that in the, let's say in the large signal picture, in the, if this current is I and this transistor is in saturation and lambda is 0, what comment can you make about this current? I. If this changed by a small amount, what comment can you make about the current in the mirror transistor? It will be the same thing, correct? So what comment, I mean, now are you able to make sense of the final result without doing any analysis at all? What is that? It's a current mirror. The incremental current being pulled in M4 into the gate of M4 is GMVD. So it's just reflected in M3. All right. Okay. So basically, this is this current therefore is what is the current through M3 therefore? GM VD flowing downwards. So what is the short circuit current Ix? 2 times GM VD. Okay. Now how does this compare with the Norton, I mean the if we did the same thing with our regular differential pair where we had resistors, this is VD, this is minus VD, this is R, this is R. In the incremental picture, this is grounded. If we found the Norton equivalent short circuit current of this guy, what would be the short circuit current? Huh? If that current is 0, why are we doing all this, man? Huh? It is GMVD. Is that clear? All right. GM. Okay. So, what is the difference between the active load and the active load that we have now and just having a resistive load? As far as the short circuit current Ix is concerned, we are getting twice the current. Intuitively, that is because the current through M1 is decreasing, sorry, the current through M1 is increasing, the current through M2 is decreasing, correct? In the circuit on the left, if small Vd is positive, then the current through M1 increases, the current through M2 decreases. That increased current is getting reflected through the current mirror, right? And you are getting and whereas what is being pulled out by M2 is actually smaller, correct? So, that difference you are getting as the Norton short circuit current, all right. So, you can see that M4, I mean that using the drain current of M1 is actually, earlier we were just simply throwing away that incremental current into the, we are not doing anything to the incremental current of M1 earlier, if you had resistors, correct. We were just throwing that away into the drain, right. Now, we are actually using that that incremental current to actually give us twice the short circuit current that you would otherwise get, all right. Now, okay. So, what the next to find the gain, we need the short circuit current as well as, yeah. So, basically, I mean, let us go back to the earlier one. The short circuit current, as you can see, is GM times Vd. We already seen this before, but I want to see it in another way. What is the Norton resistance looking in here? To find the Norton resistance looking in there, what would we do? What should we do? Deactivate the sources. So, that is Vd goes to 0, this Vd also goes to 0. What is this voltage? Incremental voltage? 0. So, what happens to the two transistors? They are just not there. Okay. So, now what is the Norton resistance? R. So, what is the gain? Gm times R times Vd is the output voltage. So, the gain is Gm times R in the earlier case when we had resistive loads. Is that clear, folks? So, now what comment can we make? Now, we will do the same thing here. What is the short circuit current? So, this is nothing but a current Ix. What is Ix? 2 times Gm times Vd, and what is the, to find the Thevenin, I mean the Norton resistance, what will we do? Deactivate all the independent sources, so that this becomes 0, this becomes 0. So, again the two transistors become, they are no longer there in the incremental equivalent. Okay. So, and what is the current through M4? 0. So, what is the current through M3 therefore? What is it? That potential is 0. So, current through M3 is 0. So, that is also goes away. So, what is the Norton resistance? Infinite. So, what is the gain? Infinite. Okay. I mean, is this you know, is this surprise or was this something that you were expecting anyway? Yeah. So, basically just like how we had in the common source amplifier with an active load, if the lambda, if the output impedance of the transistors was infinite, then we got an incremental gain which was infinite, correct. Same thing happens here. Okay. All right. So, that means the bottom line is that M4 transistor is useful after all, right, because it gives you twice the short circuit current. So, I mean, for example, if it turned out that the Norton resistance here was also R, correct, Okay. So, somehow let us say I deliberately put in an incremental resistance of R with an infinite capacitor here. How much gain will I get now here? 2 times GMVD times R, whereas with the regular resistive loads I would have got only. So, that M4 is useful after all, right. Just like when your mother sends you to anyway you are sitting at home doing nothing, right. Of course, for her gate preparation all does not count, right. Says anyway बेकार बैठा हुआ है लड़का चलो कुछ काम करवाते हैं, like go get pizza or along the way you get dahi from here and then you get some vegetables from there and and so on, right. All right. So, like that. So, this M4 is basically it turned out to be useful after all, right. Whereas, if you order on Swiggy you can't do all that, no, right. You only bring pizza, nothing else, isn't it. So, so that is the, so the basic operation is understood.